Assalamu alaikum and greetings everyone, and welcome to video 1.1b, dealing with vectors. In this video we'll be looking at how to represent vectors on a diagram, how to deal with parallel vectors and the head to tail rule in order to find the resultant vector. We'll also be looking at changing the sign of a vector or finding the change in a vector quantity, and finally we'll be looking at how you can show vectors in equilibrium on a diagram. The way you represent vectors would be as an arrow. The arrow would point in the direction of the vector, and the length of the arrow would represent the size or the magnitude of the vector. We can draw scale diagrams using vectors, and graphically we can draw diagrams to find a resultant vector, which would show us the overall effect of several individual vectors acting together, and it would give you the magnitude and direction of the resultant vector. You can either draw a scale diagram or you can draw a rough diagram and use trigonometry and basic math to calculate your resultant. The resultant itself would be shown as a double-headed arrow, and you can label it with an R. Let's first look at vectors that are parallel to each other. The steps you follow are: number 1, you assign a positive or negative sign to the original vectors given. This would mean if the vectors are horizontal or vertical, you can take arrows pointing towards the right or upwards as positive, and the ones pointing towards the left or downwards as negative. However, if the vectors are diagonal, you can assign any one direction as positive and the opposite direction would naturally be negative. And then you just add both magnitudes but without ignoring the signs. For example, if you look at the examples on the right, you have two vectors plus 3 and plus 7 being added together. The answer is naturally 10. However, in the second case, one of the vectors is pointing towards the right, positive 10, and the other is pointing towards the left. It has a magnitude of 3, but because it's towards the left and because it's opposite to the first vector, we take it as minus 3. And now 10 plus bracket minus 3 gives you 7, right? The third case has 4 vectors of magnitude 4, both acting upwards. 4 plus 4 would give you 8. If you look at the second diagram given, it does not have magnitudes, but it just gives you an idea of how the overall direction would be in the direction of the vector of greater magnitude, and how vectors in the same direction are added, but in opposite directions they would be subtracted. Now, the vectors given to you will not always be conveniently parallel to each other and easy to solve. They can be at any angle to each other. For this syllabus, you would only have perpendicular vectors, so you can use your basic trigonometry for them. The rule you would use for these is the head to tail rule. Now, if you look at the diagram on the right, it shows you a vector and it has the tail and the head labeled. The head is where the arrow points and the tail is on the opposite side. The magnitude is the length and the direction is the direction of the arrow. What you do here is you take one of the vectors and then you connect the tail of the second vector with the head of the first vector. Okay, so a tail has to meet a head and a head has to meet a tail for the given vectors. What you would do next is you would join the tail of the first vector with the head of the last vector, and you would give this a double head and you would mark this the resultant. In the cases following, you would just have two vectors, and I'll show you those in more detail. In this example, you've been asked to draw the resultant of the individual vectors A and B. Step 1 would be you mark the head and the tail for both vectors A and B. Step 2 would be you'd redraw any of those two vectors. So in the first case, I've drawn vector A first, and then I've marked the tail and the head in gray. Then I take vector B, and starting from the head of vector A, I start drawing vector B. Now make sure that for both A and B, the direction and the length of the arrows is the same as what is given in the question. Okay? And then, so for A and B, I'm following the pattern tail, head, tail, head. Then I start from the tail of vector A and I end at the head of vector B. And I mark that the resultant R, and I give it a double point because it's the resultant. For the resultant, a tail would meet a tail and the head would meet another head. Okay, I can also choose to draw vector B first, and then from the head of vector B I draw vector A. The resultant would be exactly identical to the resultant I've drawn in the first case. Okay, it would have the same magnitude, same direction. If this was a scale diagram, you could easily measure the length of the resultant and figure out the magnitude of the resultant, and you could measure the angle of the resultant using a protractor, and that would give you the direction of the resultant vector. Next up, you have 3 practice questions dealing with 3 different kinds of vectors. The first is displacement, the second being velocity, and the third is force. I've also added the 4 cardinal directions in case you don't know them, but you should know them. Another thing to be noted here is that you cannot have a vector diagram where, for example, one of the vectors is force and the other is velocity. In a certain vector diagram, you can have all of the vectors have to be the same physical quantity, right? And the resultant would also be of the same physical quantity then. Until now, we've been adding vectors in order to find the resultant or the overall net effect of all the individual vectors. Next, let's look at the change in the vector quantity, where we would have to subtract different vectors. So, for example, if you have a bus that's traveling at a speed of 14 meters per second towards the north, and then the driver suddenly moves towards the right and starts moving at a speed of 12 meters per second, what is the change in his velocity? Now, wherever you have the change in the physical quantity, you just do final minus initial. So here would be final velocity minus the initial velocity. Let's look at how we do it on the diagram. So final minus initial is the same as saying final plus bracket minus initial. And this is useful because we only know how to add different vectors. But you also know that when the vector changes direction, its sign flips, right? On the other hand, if you want to change the sign of a vector, you would have to change the direction of its arrow. So if you have initial velocity upwards and final velocity towards the right, and you want to do final minus initial, you would, first of all, you'd flip the direction of the initial arrow, initial velocity, right? And then you simply add both of them like we did in the previous example, and you draw the result. And you draw the resultant like you would normally, only in this case it would represent the change in velocity. The last thing to be considered is, what if you join vectors using the head to tail rule in such a way that there is no resultant? For example, you joined all of the given arrows in such a way that each head gets to meet a tail, and it just forms a closed loop where you don't have space to draw a resultant. This is a special case where there is no resultant. There is equilibrium, and if the vector is, for example, force, there is no resultant force acting on the object. It's like if I'm pushing a block with 5 newtons towards the right and you're pushing it with the same force towards the left, the box would not move. In case if it's velocity or displacement, it would mean that the object has returned to its original position, its original state. If it started at 14 meters per second towards the right, and you have some kind of a system of vectors where eventually there's a closed loop, it means that the object has come back to its original position with the same velocity towards the right. That's it for this video. Thank you for watching. I hope it's all clear. If you have any questions, you can hit the comment section anytime.